Oh, Mr. Hurry, look, you with the vibes.
Oh, so good.
But I got a watermelon. I like the one from Trader Joe's. The one in the big jug.
The one in the what?
Oh, yeah, big bottles. It's like in
The coconut water one?
No, watermelon.
Yeah, I like those okay, but I love the coconut. It's just
Have you ever
sweeter.
had the energy ones?
The energy buys?
Yeah. There, I got one like a couple weeks ago. It was so good. I can't find it anymore. It was like a watermelon and strawberry, and it had like 110 million caffeine. And I was like, oh my goodness.
You get them at Costco. They're so expensive anywhere other than Costco.
I haven't.
Like $2 a piece.
Yeah.
It's brutal. Costco, if you buy them by the case, which I probably have 4 cases in my car right now, then they end up being about $1.20 a piece, which is still kind of high. Feels like.
It's worth it.
But anyway.
Mr. Hurry.
Yep.
Where was that key list?
Yeah.
Yeah.
Like I will say this, in my minor defense, which is just minor. Like this is what my Schoology page looks like.
I'm kind of scared to see
Ooh,
it
who's that?
That's a nice school.
Who's that dashing young man? No, so like when you're looking at my Schoology page, this is how I miss it. So you look down there and it was there, but it was unpublished. So it looked like this. Does that make sense? So all of this is my page, like I'm trying to get ahead. So that I just forgot to publish it for you.
That's not
So
we're still really.
So we got questions for you.
So I published it this morning. So if you happen to look in the last hour or so, you saw it. But I know that you do have actually things to do here. But anyway, if you have some quick questions, I can answer them or walk you back through that. Anybody?
Yes.
Yeah, go ahead.
Yes.
Candy number 16.
So 16 on that page 303 and 4.
Yes.
So what was the question? Because I'm just going to pull up the key here.
It was a graph. It was just saying like.
Oh, so number 16 said probably graph something where the derivative was 0 in some spots, or where you had a relative max or relative min. Okay, so I think it said that it had.
I was just confused about the part about the what's that name of it?
Relative and maximum.
No, the critical number. Or it said.
Yeah, it said 4 was.
Okay, so this one, I tell you what, probably just like it. This is not the only picture that would work for this, but this is a picture that would work for it. And actually, it did show up like this in the actual written key when I finally got a hold of the written key. What page again is this? 303. Okay, so the problem asked for it wanted an absolute max at 2. So an absolute max at 2 means that at 2, that has to be the highest point. Now, it didn't have to curve like this. It could have been cusp-like, but it had to have a maximum Y value there. So I think I've achieved it with this sketch. The other thing it said was it had to have an absolute min at 5. And it also said in the original problem, sketch the graph of f that is continuous on 1 to 5. So the graph had to have a min at 5, but had to be only on the interval from 1 to 5. Okay, so that's okay because maxes and mins can occur at endpoints. If this had said a relative max or min there, I couldn't have done it. But I can get a min there at 5 at the very end at that endpoint. So I've got my max and my min in there. And then 16, it said 4 is a critical number, but there is no local max nor a local min there. Well, a critical number is a place where what? The derivative is 0 or possibly doesn't exist. So can you think of places on a function where the slope would be 0, but there's not a relative max and min? And the only thing I can think out is if it flattened out, but then instead of going back down and giving you a relative max, or instead of it came down, instead of giving you a relative min, it just flattened out for one instant and then kept going up. Or you could do it where you're going vertical. So both of those situations. So right here, I decided just to flatten out there because I thought that would be a little easier. But you could, I guess, have sketched something where it actually went vertical there. Like say it went vertical, but then went to here and then turned and still had a max there. So it could have gone vertical. You follow me, like in the red?
That's what I did.
And that's fine. This is just one possible example. And then the last thing, no, that was it. So either in the black, something like that, or in the red where it seemed a little harder for me to go vertical on that space. But I guess I could have gone higher, right? I could have, done something like this, peaked there, and then come down here and gone vertical right there, and then sketch down to the min. As long as you got the min, the max, and the critical number that wasn't a relative min or max, you're okay. Yes?
I accidentally did a wrong problem. I corrected it, but I realized that I didn't know, can something be continuous and or non-continuous and a local? Here, it's number 37. Part C. I didn't split up into those words. It wasn't a problem you're supposed to do, but it made me.
Number 37?
Or 17.
Oh, 17.
Mhm.
Sketch the graph of function that has a local max at 2 and is not continuous at 2. Yeah, that's not going to be something that AP asks. So a local max at 2, but not continuous.
Does that exist?
Well, it just depends on your definition. Like in pre-cal, it exists. But calculus, and you'll see that till Monday when we start talking about what can be achieved. But APCalc does not like to deal with relative maxes and mins or maxes and mins that aren't continuous. They just avoid it. But anyway, they're saying that at 2, there's a relative max. Is that right? There is a local max or relative max at 2, but it's not continuous. So something like this would meet that definition, right? And I guess if it's a local, maybe it's not the absolute max or something like that. But that would be local because in pre-cal, but it could also be local. In a pre-cal definition, it could be local even with this. Because isn't that y value right there higher than every y value to the right and every y value immediately to the left? Like, and when I say every, I mean, it's not higher than this one or this one. But again, a relative means even in the smallest little vicinity, is that y value bigger than ones on either side? Yes. But calculus defines a relative max as a y value where the slopes leading into that are positive and the slopes exiting are negative. Kind of like this, slopes leading in positive, critical number, slopes leading out negative. Or slopes leading in positive, critical number, slopes leading out negative. But that wouldn't be true here, would it? Those slopes leading out are negative and these are negative. So calculus doesn't like that. And that really bothers me. I mean, it doesn't bother me like I've moved on in life. But I remember when I was learning this, I was like, that's a terrible definition because I had taught pre-cal for 20 years before I started teaching calculus. And it really bothered me because we would call that a relative max in pre-cal based on the pre-cal definition. But calculus uses a different way to conclude where you have relative maxes and mins. But calculus also focuses on continuous functions more. So these piecewise things, you just don't see them as much, which is why I didn't ask you about, did I ask you about 10? Maybe I did ask you about 10. Okay, number 10, they would call B a relative max. Do you see that on number 10? Number 10 looks something like this. And this would be B. They would call that a relative max right there. Calculus wouldn't. Calculus would say, no, it's supposed to be positive going in, negative going out. It's discontinuous. We're not even going to ask you questions about stuff like that. So you don't have to worry about it. But it's bothered me. This is the same. It's not the same textbook, but it's the same author. So this same problem is in the old book. And it bothered me then. It bothers me now. But you will not see that question asked. So you don't have to worry about all these piecewise stuff when you go to calculus. I mean, when you take the AP test or take my test. I'm not going to give you those things that are like, because and you'll see on Monday when we talk about relative maxes and mins, it's troublesome. Yes.
So will you ask questions like 16 on the thing where you want us to draw a graph like that?
Not on this test, but you will have some things where we start doing curve sketching. That's our next chapter. So I'm going to give you all the information you need to curve sketch in this chapter, and then we're going to focus on it in next chapter, actually putting it all together. But you'll have more information. Like you'll have information like, oh, on the interval from 1 to 2, the slopes are positive. So you'll know the graph is sloped upward. And then I'll say, yeah, on the interval from 2 to 5, the slopes are negative. Oh yeah, look, they're just sloping down negatively. And then I'll say, yeah, there's a relative max here, a max there, a min there, whatever. And you'll take all this stuff and start piecing it together. And you'll learn about concavity. So you'll know about stuff like using derivatives and second derivatives. You'll know when over what interval is it concave down or concave up. Like right here, that's concave down. Right here, that's concave up. Right? This concave down. You'll learn about all these things and you'll piece them all together. And it's really, it's not amazing like a flower bursting forth from a seed, but like in terms of math, it's amazing that you can actually take this information and sketch really weird graphs. Then you pull up your calculator and you're like, I'll be darned, money. I don't even need a calculator to do a lot of these things anymore because the calculus tells you about all the movements and critical numbers and concavity and slopes and everything. And you can put it together and actually graph pretty decent curves.
See, I was looking forward to drawing like crazy.
Well, there will be some really ugly ones on there that you'll have to graph and put it all together. Take everything you know about vertical asymptotes and holes and relative mins, all this stuff. But by the time we get there, hopefully it won't be as daunting as maybe on day one. Anybody else on this?
Number 41. All right, I'll get that later.
41. So
It's at the bottom.
okay, so 41, I think just asked for the critical numbers.
You got the top right, but in the bottom,
Like this?
what do we do? You have to set it equal to 0, then what?
Yeah, you can set equals 0, but I just looked at it and I realized it was going to be imaginary. Like if you try to solve that, I probably should have been more clear and written everything out. But I wrote does not equal 0 for real values of y. It doesn't equal 0. Like you can try it. Like if I told you to solve that right there, you'd say, oh, quadratic formula, right? Negative b plus or minus, and then you'd come in here and go -1 squared, which is 1, minus 4 times a times c. Well, I get -3 there. Well, that's an imaginary number. Well, if it's imaginary, it's not in the domain, is it? Right? And remember, to be a critical number, it has to be in the domain. Well, that very same value is the one that I'm setting equal to 0 to find out where the derivative is dne. So what I probably should have done is been more clear in my key. I showed you where it was equal 0. I probably should have said the derivative of g of x does not exist when, and I probably should have said y squared minus y plus 1 squared equals 0. And then you could say there are no real values here. But all I did was check the quadratic formula to see that. And if you remember back to algebra 2, you remember the discriminant? The b squared minus the 4ac part of the absolute value? That's really all you have to check. If the b squared minus the 4ac is negative, what are you going to end up getting? An imaginary. So rather than go through the whole motion, I just eyeballed it and went, wait, the b squared is 1. If I subtract a 4ac from it, I'm subtracting 4 from 1. That's negative. That means my answers to this are imaginary, so there's no real answers. So there were no critical numbers. Now, if I put a different number in there, like if I make that y squared minus 2i plus 1, then it's a double root. I get 1 as an answer. All right? Or if I change that positive 1 to a positive 2 or something else, I mean, I could change the numbers and get roots. But if I see that there is no place that exists, then sometimes I might skip a step. And you'll see the keys do that. If they look up there and go, wait a minute, there's no real answers there, you're not going to see them check that. They're going to just check the place where there are real solutions. Does that make sense? Yes, no? But yes, for critical numbers, I should be checking both. I just maybe got a little sloppy there, got a little lazy because I did check it. I knew they didn't exist in the denominator. So obviously the denominator squared is not going to exist, right? So I just moved on. All right. Yep.
Sorry.
It's all right. Now we got to move on. Anything else? Come see me in the morning. Go ahead.
Can you show me 51?
51. So 51 said using a calculator, formula for the derivative is shown. How many critical numbers? Okay, now, again, we haven't talked a ton about calculators. We will. But what do we do to find a critical number? We find where the derivative is 0. Well, what if I give you the derivative graph? Then couldn't I graph it and see where it's 0? So on 51, there's my graph. Where was it 0? There. Right? I mean, they gave you the derivative. Right? If I gave you the function, you would have to look for what? Places where you had relative mins. Those are where the slopes are 0. Or places maybe where you had go verticals or cusps. Those are places where the graph doesn't exist. You would have to look on the graph for that. But if I give you the derivative, this is the derivative function. I don't know what the original function was, right? They said that right here, this was f prime. So who knows what f is? Who cares? If I want a critical number, I just want to know where the derivative is 0, which is kind of nice, right? I just look where it crosses. And for the record, your calculator, you'll see soon, you can, if I have the regular function, I can graph the derivative. So for all these problems where I said, where are the critical numbers? And you had to do all this derivative work, right? You could have just graphed this derivative function. You don't even have to find it. Like the calculator will graph it for you. You just write ddx and you type in the function and you graph it. And you can just look at it then and go, all right, where did this graph hit 0? And all those zeros are critical numbers. All of them. Now, you'd also have to look and say, are there any cusps? Were there any corners? Does it go vertical anywhere, right? Or is there a vertical asymptote there? Or a hole? Those things you'd have to look for also, but not usually in calculus. Usually in calculus, it's a continuous function. So all you're doing is looking for those zeros. But we'll do a ton with that later. Good questions. All right, we're going to jump to something new today. And we're going to really pick up with what we did yesterday on Monday. But I'm going to insert something in here. You're probably going to need a calculator. I think we're going to have time to get to everything I want to get to. So since we're not pep rallying it up today. Yeah, you'll probably need a graphing. And I've got some over there if you want to borrow them. But I want you guys to turn to the mean value theorem, notes day 2. And this is going to be your second major theorem. Okay, guys, I got to tell you, every year I am befuddled as to why people make this hard. So if you find that it's hard, don't feel bad about it. Try to tell me why. Because to me, the mean value theorem is one of the easiest things to do and even to check on this test, on the AP test. And there's very few ways for me to ugly it up. It's like there's only a handful of ways to ask questions about the mean value theorem, and they all look pretty similar. It's like a red flag just comes bursting out of the ground, smacks you in the face a couple times, and all you got to do is remember how to do it, right? It's not a tough process. It usually involves a basic derivative, usually something like a power rule, and a slope. That's it. And if you can do a slope, y minus y over x minus x, and you can do a basic derivative, you can do the mean value theorem. It really is not overly technical. But for some reason, it just beats people down. I really don't get it. So every year I ask this question. Rarely do I get any responses. But if you're struggling with it in any way when I get done talking about it, just tell me. Okay, this is the part that really bothers me because I really genuinely want to know why. So let me just throw it out there at you. All right, mean value theorem. This was a review problem, but we've already kind of done one. So I'm going to jump to mean value theorem. All right, so the mean value theorem says this, and I'm going to describe it first, and then I'm going to go back to the formula. The mean value theorem says, all right, if you have a continuous function, all right, on a closed interval, so that means you have to be going from a point at A and a point at B, right? There can't be holes at the end or VAs at the end, right? So if I have a continuous function on a closed interval, that is also differentiable on the open interval. That means endpoints, you can't take a derivative at an endpoint, but everywhere else you could. So continuous on the closed, differentiable on the open. Those are your conditions. Kind of like the conditions on the EVT where you had to have a continuous closed interval. We'll just add that, add to this, or add to the EVT. Yes, you have to have a continuous closed interval, but also a differentiable open interval. Now, before I go any further, what does differentiable open interval mean to you? If it's continuous and also differentiable, what can't be there? Can't go vertical, can't have a cusp, can't have a corner. And we already said it was continuous, so you don't have to worry about the other stuff. Are you with me? So that really just leaves you with nice little curves. All right? Now, if those conditions are met, the mean value theorem says this. From your first value of, I call it point A. I know my graph goes a little further, but that's because I'm using a program and it doesn't let me chop it there. So you can ignore this, but from A to wherever B is on that closed interval, from A to B, there's a slope. And you remember I mentioned it and I gave a bonus question on it. What do we call the slope from beginning to end of a curve? The average rate of change. Slope from beginning to end. Y minus Y over X minus X. Average rate of change. That slope there will happen to exist somewhere else on the curve as you're moving along at least once. It's guaranteed. And you can see that right here. That slope of that line, as I start at A, well, it's not the same, is it? That slope and this slope are different. As I start, it's different. But at some point, what happens? The slopes match. Now, how do I find the slope right there? That's not an average rate of change. What is the slope of a curve at a particular point called? That's it. The average rate, the mean value theorem, and mean means average, right? Right? Average rate of change. The mean value theorem says that the slope from beginning to end, which is the average rate of change, is guaranteed to equal the slope somewhere on the curve, which we call the derivative or the instantaneous rate of change. At least once. And we use C to say there is some X value, at least one, where that would occur. And if I just do this process, I'll find it. So literally all this is saying to do is take your A and your B value and find the 2 points. And you can find the Y value that goes with that A, right? Plug it into the function and find the Y, get that point. Plug the B into the function. And I'll do some of these. You'll see it's not a big deal. I hope it's not a big deal. I'll plug the B in and get that point. And then I just use the Y minus Y over the X minus X to find the slope. And then for the left side, what does it look like I'm telling you to do? Find the derivative. So you literally pull out your derivative rules and you calculate the derivative. Now your derivative is going to be a formula, right? It's going to be a new equation. Plug that new equation in there. It will be equal to a number and just solve. That's it. And when you solve, the X answers that you get for X will be those C values where the slope at that spot matched the slope from beginning to end, where the instant rate of change matched the average rate of change. Does that make sense? It's kind of like this. What if I told you I drove from here to Colorado, 1,400 miles, right? And I averaged 55 miles an hour. That's my average rate of change. Well, what does that probably mean in my journey? I probably stopped some. By the way, if you can average 55 from here to Colorado, you are probably either A, never going to the bathroom, and B, speeding like crazy. Like when I put my kids in my car, we went on long trips. We used to drive to Arizona and California and Colorado all the time. We would just hit national parks and do whatever. And when I had them in the car, I mean, I would allocate water. Like they were so dehydrated by the end of the day. Because if you have 3 kids and they're like just glugging water, and my wife's always drinking. I mean, we were stopping every 30 minutes, and it killed me because you stop and it's like, oh, I want to get a snack, whatever. And every time you stop, it's 15 minutes. So it was like, take a sip. Okay, back on the road. And we would make great time. I remember we averaged once. It was like on the day we averaged close to 70 miles an hour. I mean, we were killing it. Like we zipped through a drive-through, grabbed the food, threw it in the back, kept going. Just ate on the road. We didn't stop for anything. I was like, I'm getting home. But the point I was trying to make is if my average rate of change is 55, more than likely I went a little bit slower. Maybe I stopped a couple times. More than likely I was speeding sometimes. But what was guaranteed? That at some point on that journey, I went what? 55. That's it. And that makes sense, doesn't it? Because to go between a low and a high speed, you're going to have to hit the middle. Now, would that be true if actual cars didn't have continuity? If I could somehow go 20 miles an hour, 60 miles an hour, I can't push a button and jump from 20 to 60, can I? That doesn't work. I've got to go through all those. Right? Now, you might feel like you can if you have a nice enough car, right? 0 to 60 in 4 seconds. But I literally went through every speed to get there, didn't I? So the point is, that's all we're saying. So if you look at this, and I'll show you this example right here, and you don't have to use C as your variable, and I'll show you it with X's. If you want, you could just stick with X the whole time and get your X, but that's what they're referring to as C. So here's an example of this problem. Here's a parabola. That parabola on the interval from 1 to 2 has some average rate of change, right? I don't know what it is because I haven't graphed this parabola and I haven't looked at it. So all I'm going to do is I'm going to see, did it meet the conditions? What were the conditions for this mean value theorem to work? It has to be
Differentiable on the open.
Well, first, continuous on the closed, just like EVT, right? And sure, it's continuous. It's a parabola. All polynomials are continuous, right? And I have a closed interval. Is it differentiable on that same thing, on that same interval? Well, of course, because all polynomials are differentiable. Do you ever see a cusp on a polynomial? No. Do you see corners on those? Right? So if I know that all polynomials are always continuous and differentiable, right? And I've got a closed interval, then I know that my conditions have been met. So all I have to do is find the slope from beginning to end. Now, how do I find the point that goes with -1? I plug -1 in the function. That's f of -1. How do I find the y value that goes with the 2? I plug 2 in the function. That's f of 2. And then I subtract the y's, subtract the x's. That gives me the slope from beginning to end. That's it. Are you with me? So literally, I found the points. So plugging a -1 in, I got a 17. No, I didn't. I got a 14. And plugging a 2 in, I got a 17. So I just went 17 minus 14 over 2 minus the -1. That's literally all I did to find the average rate of change. Yeah.
So A and B is just like X and B.
Yes. Yeah. When I say interval from A to B, no. It's not X and Y. It's X to X.
Yeah, it's like.
Yeah. When I say interval from -1 to 2, I'm talking about. So when I say that -1 to 2, I'm talking about X values at the beginning and end. So you plug them in and find Y values. And thank you for asking that question. Those are the kind of things I need to hear. Yes.
On this test, we'll be able to use calculator all the time.
I don't know. I'm not that ahead. Now, what do I set this equal to?
Set it equal to
The derivative. So calculate the derivative, which is 8x minus 3. Shove that in there. So you end up getting an 8x minus 3 on the left. You end up getting a slope of 1 on the right, and you solve the equation. And when you solve the equation, you're going to get an x value. Now, sometimes you get lots of x values. You might get like x equals a half, x equals 7, x equals -4. And if you get a bunch of them, or even one of them, make sure your answers are on the interval. Like sometimes, remember, the curve is the curve. The curve might be going way past that interval. So if I got those for answers for x, I would go, oh, -4 is not in that interval, 7's not in that interval, but 1/2 is. But you are guaranteed to get at least one. Why? It's the mean value theorem, right? So the average rate of change has to match the instantaneous rate of change at least in one spot. And that's all we do to do it. Yes?
So can you go back over how you got the AX or
To get the what?
AX minus?
Yeah, that's the derivative of this. So literally, remember, this formula says take the derivative of your function, which is 8x minus 3, right? Take that derivative and replace it here. There's my 8x minus 3. I just used c because most textbooks say find the c value. They'll say find the c value that's in that interval. But remember, all these things, c, a, b, they all refer to what? X values. They just give them different names to suggest that they're actually in different spots. They could have said x1, x2, x3 or something like that, but it might have been better to say that, but they don't. They say a, b, and c. Are you with me? All right, what about this? So this right here, that means on this graph, I do not know. Actually, I know a little bit if you think about it. I know that at -1, I was up here at 14. I know that at +2, I plugged that in and got 17. So, and I also know this is an upward sloping parabola. So, and this tells me at +0.5, this is what, 0, 1. So at +0.5, the slope here, that's the average rate of change at +0.5 matched it. So I'm guessing this parabola looks something like this. Because the average rate of change matched the instantaneous rate of change at 1/2. That's all it's saying. It's like, I don't think that's a big deal. Maybe you do. We'll see. All right, Rolle's theorem. Rolle's, it was funny to me. Rolle's is just a stealer of theorems. Rolle's, and you're going to see this. Like, I don't know. I'm sure he was a smart guy. But it's funny to me how Rolle's puts his name on his theorem when all he really does is talk about the mean value theorem in one special place. Rolle's looked at it and said, hey, look at this. If your points at the end, your A and your B at the endpoints, if those have the same Y value, he says then you're guaranteed to have a slope somewhere that's 0.
Whoa.
That's great.
But all he did was say, if the points have the same Y value, what does that mean? That your average rate of change is 0. Well, then your instantaneous rate of change has to be 0. And he evidently thought that was so impressive. I'm going to put my name on that. I don't know why he didn't put his name on the mean value theorem, right? And then just say this was just some little extra little addendum to it or something. But all Rolle's is saying is this special condition. So Rolle's literally, same conditions as before. If it's continuous on a closed interval, I've had that on everything, right? And differentiable on the open interval, just like the mean value theorem. He just takes, he takes the mean value theorem, right? This is mean value theorem. The derivatives at a particular spot is going to match the average rate of change, or the slope from beginning to end, right? That's the mean value theorem. So this is what Rolle says. Hey, wait, what if your f of b and your f of a are the same? Well, if they're the same, then what happens when you subtract them from each other?
0.
And 0 over anything is what?
0.
So literally, Rolle says, if those two things are the same, then the derivative equals 0 somewhere. Where? I don't know, but you can solve and find out. I mean, it is the theorem least worthy of putting your name on it in all of calculus, I think. But anyway, that's Rolle's. But you don't even have to quote Rolle's. You can just say by the MVT. So it's one less thing you can, and I'll probably on your test ask you like, what's Rolle's, what's MVT, and you'll have like multiple choice or matching or something like that. Or maybe I'll give you a true false statement and say, is it true? If yes, say true. If not, and tell me what's wrong about it, or make it right. So I might give you some stuff like that, so you'll have to know the difference. But really, rolls is just the MVT. When these are equal, it gives you 0, so the derivative is 0 somewhere. And you can see that, right? When you have the same y value, when f of a and f of b is the same, then the average rate of change is 0. The slope somewhere at some c value is 0. And again, that x right there is like the c value. So you literally do it the same way, except you don't even have to find average rate of change. But you do have to do this. If I say, how do you know for certain that there's a slope of 0 somewhere on this curve? Well, that there's an instantaneous rate of change. An instantaneous rate of change is 0. How do you know for certain? What 3 things would have to occur? Continuous on a closed interval, differentiable on an open interval, and how do you say that? The f of the a would have to equal the f of the b.
You know who Rolls is? He's the kind of guy that you tell a joke to, and then he says the joke loud for the rest of the class.
He gets credit for it. Yes! Hated that guy. Yeah, you guys, you whisper to it, and he's like, and then he yells, yes.
What a joke. He needs to assume.
All right, now, guys, right here. Notice right here, average rate of change look like a 0. Do you see a 0 anywhere on this curve? Nope. Did calculus just break?
Nope.
No, it didn't meet the demands, right? The conditions were what? Differentiable. That's a cusp or something like that, a corner cusp. Right here. Slope 0, but I don't see a slope anywhere 0. It's not continuous. So if you ever get a situation where you go to solve the mean value theorem, whatever, and you look at it and you're like, crud, I didn't get a C value. I didn't get one. Then what probably happened is either maybe you made a careless math error, or maybe the graph didn't meet the conditions, which is totally possible, right? And you just weren't noticing that. So right here, here's a question you might see tonight. Verify Rolle's theorem for this interval. Well, what 3 things do you have to do to verify Rolle's theorem? Okay, I got a polynomial, definitely continuous, definitely differentiable, and I even have a closed interval. So those conditions have been met. What else? The y values have to be the same. So since my interval is -2 to 2, I got to find f of -2 and f of 2, right? I'm finding the y values at the endpoint. So I plug a -2 in there, and I get 16 plus 16 minus 8 is 8. And I plug a +2 in there and get 16 minus 8 is 8. So I have the same y values. So all 3 conditions were met, right? So how do we know there's that? It was continuous on the closed, differentiable on the open, and f of -2 and f of 2 were met. So I know there's going to be one. So what do? Take the derivative and set it equal to 0. It's almost like finding a critical number, right? Which is essentially what you're doing at this point. So this is a little easier than mean value theorem, because on the mean value theorem, you would have to do what? You would have to take the derivative and set it equal to the average rate of change, which would be y minus y over x minus x, which you can still do, right? But what do you end up getting? 0, which is why that's the one distinguishing characteristic that Rolle's has that the mean value theorem doesn't have to have. So you go to solve, and most of the time the factoring's pretty basic. You can see it. Take out a 4x, difference of 2 squares. Did Tyree say diff ta qua or something like that? Diff to. I've never heard that until this year. But she's been saying that? Okay. Because these 3 girls in my 5th period are always saying diff to squad. I'm like, what are you talking about? I'd never heard that. But anyway, you get 0, -1, and 1. But remember, what's the interval? Go back and make sure. If there's just 1, you know there's got to be 1. You're fine. But if there's more than 1, just make sure they all fit in there. In this case, they do. So yeah, at those 3 C values, that's where the Rolle's theorem was met all its conditions. Yep. Yep.
Are you gonna ask us to graph it? Not the rolls, but the MVT.
I mean, I have seen AP questions that maybe look something like this. and they have all these like A, B, C, D, E, F. And they say, at what locations would the mean value theorem, at what X values would the mean value theorem be affirmed, or something like that? And then you would go, well, let's see. The average slope from beginning to end kind of looks like that, right? So where do I see that slope occurring? Maybe right there at B, and maybe right there at E. Does that make sense? So at B and E, it looks like the instantaneous slopes were the same as the average rate of change, or the derivatives were the same as the average rate of change. That's a question I've seen, but you didn't really have to graph it. You just had to visualize that. And that's a good question to understand. Y'all see what I'm doing? And usually it's fairly clear. Rarely would it be like, I mean, they're not going to do this and go A, B, C, D, and make it where it's really hard to tell which letter goes with what. It's usually pretty obvious. All right, let's check out another Rolle's theorem right here. This one has a vertical asymptote in it, right? Oh, wait, vertical asymptotes means it's not continuous. Well, maybe at that one spot. What one spot is it not continuous? 15/8. And what's 15/8? Or if you don't see that right here, if you don't,
1.87.
always hit the wrong button there.
Just heard.
Hold on one second. So right here, if I set 8x minus 15 equal to 0 and solve, I get 15/8, which is about what? It's just shy of 2. Is 2 in this interval? So do you have to worry about this VA? No, because this is basically saying we only care about what happens on this graph between 3 and 5. Over here at 2, your VA is over here. I don't care. So this doesn't bother me. It's still continuous on the closed interval. It's going to be differentiable because remember, all rational functions and all polynomials are continuous and differentiable where they exist. So as long as that thing is out of the way, not in the interval, I'm good. But Rolle's also makes me check what?
It's the
Y values at the beginning and the end. So I plug a 3 in there and get 9 over 24 minus 15. And 9 over 24 minus 15 is 9 over 9, so 1. And then I plug a 5 in there and get 25 over 45 minus 15, which is 40 minus 15, which is 25 over 25, which is also 1. So the Y values are equal. So it was continuous on the closed interval. By the way, don't say continuous on a closed interval. If you have the closed interval, say continuous on bracket 3, bracket 5. Don't say closed interval because they're going to go, which closed interval? Are you with me? If you know it, specify it. Differentiable on the open interval. F of 3 equals F of 5. So I am ready to go. What do I know for certain then?
You're gonna get one.
The derivative of this will what? Equal 0 somewhere. So I took the derivative, you can see it right here. I took the derivative of the function low times d high minus high times d low over the low squared. It is guaranteed to equal 0. So this is my f prime of x. This is my equal 0. And where is that whole thing equal to 0? I got to FOIL that or distribute that stuff, add like terms. This is only 0 when what? When that's 0. So I take that, set it equal to 0, factor out of 2x, and I'm left with 0 and 15/4. But look at that 0. Not in the interval. If there was just one answer, guaranteed to get 1. But if there's 2, check the intervals and make sure there's not an extra one. Heck, check them all the time. Because sometimes you make math errors and it's just a way to catch a mistake. You with me? All right, what do we got?
5 minutes.
5 minutes? Look at an AP problem. Right. Let me just do this. I'm going to skip that and go to the graphing calculator example. What if This is how you're going to need to know how to use your calculator a little bit. What if you're doing mean value theorem, right? And you do the average rate of change on the right side of the equation, which is where I normally do it, and you get 8. Sweet. You plug the 8 in. And then you take the derivative of the function and you get this. And then you look at it and you're like, okay, now I just got to solve, right? So most people know, you should know after Algebra 2, Algebra 1, Algebra 2, and pre-calc. Most people know if I'm solving a polynomial equation, I got to set it equals 0. So I set it equals 0, and now I'm here. And you're like, crap, that's not a square. If it was squared, I could use quadratic formula. I don't know how to factor this. I really do not want to take out my possible rational roots and start checking them one at a time. And I've never seen an AP problem where I had to do that. It's possible I could guess, check, and revise. Like I might get really lucky by plugging a 1 or a -1 in there and it's actually true. But I look down and I'm holding my calculator. And I think, how could I use this calculator to help me? So here's what I do and what you need to be able to do on this test. And you can do this even if you can factor and solve, but you're going to need to be able to do it when you can't. All I have to do right here, guys, is replace the 0 with a y and then graph that. And when I graph it, guys, I don't know what it's going to look like. It's going to be some cubic, right? Right? Cubics sometimes cross the x-axis. And if they cross the x-axis, guess what the y values of those points are? 0. So literally, to solve this equation, move everything to one side, put a y in there, graph it, and find your zeros. Does everybody in here know how to find zeros? Using like the second calculate feature if you have a 84, or using the menu button on an Inspire where you just go menu, analyze graph, find the zeros. Does everybody know how to do that? Okay, we'll see if I can get this in. So right here. Oh, nice. So let's just say I have my calculator. Guys, I'm going to go to the graphing part. I'm going to go to the graphing part right here. Get some focus here. I'm going to hit tab and I'm going to graph. What was the equation? Somebody tell me. 3x to the third minus 2x. Oh, goodness. 3x to the third minus 2x, what? Minus 7. Have no idea how to solve this. But look, I've got it typed in. I'm going to make my window just a standard zoom. I'm going to graph, and oh my gosh, it crossed at one spot. What was my interval they gave me, by the way? On this problem. Oh, I didn't give you, did I give you an interval? So let's just say the interval was -10 to 10. Well, it doesn't matter if it crosses anywhere else. If all I do is graph the interval that's this mean value theorem or whatever is showing up on, I can see where it crosses. Don't say 1.5. You got to be accurate to 3 decimal places, right?
Would you want to set your window to the interval?
I would definitely set my window to the interval because then I'm not distracted by any other junk, right? So set the window and just go menu, analyze the 0, and I'm going to pick a left bound, and I'm going to pick a right bound, and there it is, 1.493. And do y'all know how to do that with the 84? Okay, with the 84, you type it in, and once you have it graphed, you go, it's already on there, go second calculate, and then just pick 0, and then just pick something from the left and something from the right. So like that, here's a square, it's not a square graph, it's cube. You have these two. So you have a graph. You can see it's going to cross at about 1.5. All right, so then you're going to go, now let's graph. Second, calculate the 0. And then you're going to pick something to the left. Let me guess. 1, enter. Something to the right. 2, enter. And there's your 1.4. Yes, that's not. There's your 1.49. You're trying to ask money from your poor teacher?
I'd like to purchase a cup off of you.
I don't have any coffee. Oh, just a regular
I
cup?
just want the cup. You want me to just-
Can I have?
All right, homecoming attendance. Good luck tonight.
Mr. Cocoa Pack?
Yeah.
2 in 1 class.
Mister, are you gonna be there, right?
I don't know. I didn't thought about it. I haven't talked to my wife. It's nice weather. I'm like,
I think you should
if it's
come
raining,
see the
I probably will not.
I think you should come see the band and then you should wait for me because I'm obviously your
I know.
favorite
You gotta
band.
keep in mind, I've gone to 29 years for the football games.
Oh, yeah.
29 years for the pep rallies.
That's awful.
At some point, it's like,
Not really short classes.
It's awful to me and I'm
what's that?
17.
You have a hot cocoa packet? Just to eat
Just to
plain?
eat the package.
There may be one in there. Just probably not big.